Hello everyone, I am Art, a student at ETH Zurich, and I will present the joint work with Martin and Chenda on multi-threshold asynchronous reliable broadcast and consensus. Broadcast and consensus are two of the most fundamental primitives in distributed computing and have been studied extensively. These protocols, however, take a different form depending on the underlying model. Here we consider the case where the network is complete, meaning that all parties have a direct channel to every other party, asynchronous, meaning that the messages in the channels can be delayed arbitrarily, however each message sent is eventually received, and finally the channels are assumed to be public, meaning that the adversary can read all the communication between the parties. Next, the adversary is assumed to be a central entity who can corrupt some of the parties, which is denoted by F. The adversary is assumed to be Byzantine, meaning that he can make the parties behave in any arbitrary manner. And finally, we assume the adversary to have unlimited computational power. That is, we argue about security in information theoretic sense. In these classical protocols, the security guarantees are typically provided in all or nothing fashion. If up to T parties are corrupted, all security guarantees remain. However, if more than T parties are corrupted, the protocols do not provide any security guarantees. On the other hand, multi-threshold protocols are a generalization which provide different security guarantees depending on the amount of corruption, thereby allowing a graceful degradation of security. We consider both reliable broadcast and consensus protocols, and we consider separate thresholds for each of the property guarantees, namely validity, consistency, and termination. Our work shows a very complete characterization for both primitives, what is achievable and what is impossible. We start with broadcast. Broadcast allows a specific party, which we call a sender, to distribute a message among recipients. Typically, broadcast is defined in property-based manner. In this talk, however, as I mentioned before, we consider the generalization of this definition. Namely, we consider now for each property a different threshold. More precisely, if the number of corruptions is below some separate threshold TV, then we want the protocol to achieve validity, which basically states that if the sender is honest and broadcasts M, then every honest party that outputs M. Second, we have the consistency property. Again, here we consider a separate threshold. If the number of corruptions is below this threshold, then we want the protocol to achieve consistency, which basically says that even if the sender is dishonest, then no matter what the sender does, the honest parties output consistently some value M prime. Finally, we have termination. And here again, we use a separate threshold, TT. And as long as the number of corruptions is below TT, then we want the protocol to achieve termination. Note that in broadcast in asynchronous setting cannot be implemented with guaranteed termination. This comes with a simple observation that the recipients cannot distinguish whether the sender is corrupted and doesn't start the protocol or the messages are simply delayed. Therefore, what is typically required is a weaker property known as partial termination, which states that if the sender is correct, then all honest parties eventually terminate. However, if the sender is corrupted, then either we require that no one terminates or everyone terminates and outputs a value. The first result of this work is the following theorem, which gives a complete characterization of this primitive. Multi-threshold broadcast is achievable if and only if maximum of TC and TV plus 2TT is smaller than N. This generalizes the known result where a single threshold T is considered for all the properties, and broadcast is achievable if and only if T is smaller than N3. First, I will show a protocol that achieves this bound. We start with Braha's protocol, which is optimal in case of a single threshold T. Braha showed that this algorithm here solves the broadcast protocol for up to T smaller than N3, which is optimal. Now, with a little bit of thinking, one can easily generalize this for separate thresholds as follows. Instead of N minus T, we replace this with N minus TT. T plus 1 is replaced with maximum of TC and TV plus 1. And finally, again, N minus T is replaced with N minus TT. However, This only works for the case where TC and TV are above TT. The main problem is that the termination property in Braha depends on the consistency property. Braha's protocol cleverly solves the termination problem by making sure that the ready messages are amplified among the parties. More precisely, if one party outputs a value in line 4, then he received n minus t ready messages, from which t plus 1 ready messages are sent from honest parties. Now, in the line 3, all honest parties will receive those ready messages and will send a ready message themselves. This is also known as amplification of ready messages. This way, Braha's protocol makes sure that eventually every party will output a ready message and will terminate. However, this technique works as long as the ready messages are unique. If TT is above maximum of TC and TV, then we have cases where this is not achieved, and therefore some parties don't terminate. To solve this, we have to come up with a technique where the parties agree to terminate, even if they don't agree to output a value. And the way this is solved is the following. Now, in addition to the ready messages, parties also send a message with a terminate flag, which basically states that the party is willing to terminate. However, we still want to achieve consistency and validity. Therefore, we require in line 4, besides the ready messages, besides the terminate messages, at least maximum of TC and TV plus 1 to be ready messages that they agree on a value and prime. One can then show that this protocol here achieves multi-threshold broadcast protocol as long as maximum of TC and TV plus 2TT is smaller than n. The other direction, if the proof is simple, we divide the proof into different bounds. First, we have to prove that TC plus 2TT is smaller than n. In this talk, I will show only the first part. The other part is very similar, so we won't go into the details for the other bound where we can show that TV plus 2TT is smaller than n. The proof is by contradiction. Suppose there exists a multi-threshold broadcast protocol with TC plus 2TT equal to n. We partition the set of all recipients into 3 sets, A, B, and C, with sizes A and B sizes TT and C of size TC. Now we build the network as in this picture, where we have 2 independent runs of the same protocol. On the left side, where the sender broadcasts a 0, and on the right side, where the sender broadcasts a 1. The notation here between A and B means that all the messages between A and B are delayed. Now, because all parties here are honest, only these messages here are delayed, and A and B have size TT, then because of termination property, one can argue that all the parties here will terminate and output. Since all parties are honest, then everyone here outputs a 0. In particular, parties in A output a 0. With the same argument, all parties in B output a 1. But now consider the attacker that corrupts the sender and the parties in C and emulates the protocol as in this picture. Now, since the configuration is exactly the same, again, we can argue that A outputs a 0 and B outputs a 1. But this is a direct contradiction to the consistency property. Next, we go to the second primitive, namely consensus. In consensus, the goal is to reach agreement on a common value where each party has an input. Similar to broadcast, we consider now here multi-threshold consensus. So if the number of corruptions is below some threshold TV, then we want the protocol to achieve validity, which basically says that if the parties have pre-agreement, then they keep this value. Secondly, we have the consistency. Here again, we use a separate threshold TC, and consistency in consensus basically means that if the parties start with some input, if they output consistently. No matter what value epsilon, as long as it is the same for every party, then the protocol achieves consistency. Finally, we have termination, and which basically states that eventually every honest party starting with xi outputs some value epsilon I. Here we distinguish between 2 types. One is with probability 1 minus epsilon, and the other one is almost surely. First, we will just concentrate on the 1 minus epsilon case, and in the end, I will briefly explain the main obstacles that one encounters for the almost surely terminating case. Okay, the next result of this work is the following. Multi-threshold 1 minus epsilon consensus is achievable if and only if maximum of TC and TV plus 2TT is smaller than n, and 2TV plus TT is smaller than n. As we can see, the first bound is similar to broadcast. It's the same as in broadcast, but the second one mainly comes from the definition. The protocol is more complex, so I will give only a high-level idea. We start with Ben-Or, which works in fail-stop model for corruptions up to ½ The protocol is simple, but due to the randomness and non-determinism, it is not straightforward to analyze. The main challenge in designing of the algorithm is the case where the number of corruptions is above ½ The first problem we encounter is with respect to coin. If the number of corruptions above third, even when all honest parties obtain the same value V as local coin, the adversary can schedule messages so that the majority decision among n minus TT parties is inconsistent. And this prevents the parties from terminating. Finally, as pointed by Aguilera and Toig, the global variant of the Ben-Or doesn't work for the case where the number of corruption is above ½ To overcome this problem, we divide the protocol into the deterministic part and the randomized part, and by adding an additional round to Ben-Or protocol. This, however, works only for the fail-stop model. For the Byzantine case, we borrow the technique that Braha presented, which is basically correctness enforcement scheme. If we plug this correctness enforcement scheme into the modified Ben-Or protocol, then this works as long as termination threshold is below maximum of TC and TV. If TT is bigger than maximum of TC and TV, then correctness enforcement breaks down. The protocol reaches inconsistent states and gets stuck. This is solved by introducing a different correctness enforcement, which basically makes possible that if inconsistent states are arrived, then these are eventually detected. However, to solve this, then we had to fix the number of rounds, and as a result, we can only guarantee outputting a message only with probability 1 minus epsilon. However, for this, the parties still cannot guarantee to terminate, and eventually they might never shut down the computer. So to make also possible termination, we add on top of this a termination protocol, which is very similar to broadcast. And in this way, we then build the consensus protocol, which terminates with probability 1 minus epsilon. Finally, the impossibility proofs are very similar to broadcast, so we won't go into details. About the almost surely terminating consensus, we show that this is possible under the same bounds if we assume a global coin. However, without such an assumption, we give only a construction as long as TT is smaller than n3. Whether this is necessary is left as an open question. Thank you very much.